You know the planets. You learned them as a kid, maybe with a mnemonic, maybe from a poster on a classroom wall. 8 worlds circling our star. Mercury through Neptune. The list felt complete. It felt finished. It might be wrong. In 2025, a team of researchers published a mass estimate for a planet no telescope has ever photographed, 4.4 Earths, orbiting so far from the central star that it takes between 5,000 and 20,000 years to complete a single lap. The last time this object was closest to us, humans were building the pyramids, or hadn't invented farming yet. If this world is real, then every diagram of the solar system you have ever seen is missing a planet. We grew up with a map that left out something 4 times heavier than the ground beneath your feet, and nobody noticed for the entire history of telescopes. The evidence stretches across 2 centuries of searching and includes a photograph that may have been sitting in a government archive since 1983. None of it is simple. All of it is strange. So, how did we get here? And why, after 200 years of being wrong about what hides beyond Neptune, does the case keep getting stronger? In 2025, a team at the California Institute of Technology published a number, 4.4 Earth masses, plus or minus 1.1. That is the estimated weight of something orbiting our star at a distance so vast that light from Sol takes more than 2 days to reach it. No telescope has ever photographed this object. No spacecraft has visited it. And yet the number exists in a peer-reviewed paper funded by NASA, built on over a decade of gravitational evidence. The semi-major axis falls between 380 and 460 astronomical units. 1 astronomical unit is the distance from Earth to the central star. At 380, you are roughly 10 times farther out than Neptune. The orbital period sits somewhere between 5,000 and 20,000 years. That means this object, if it exists, last occupied the part of its orbit closest to us sometime around the construction of the Great Pyramid at Giza, or possibly earlier. The Caltech researchers did not call a press conference. They published updated calculations refining a model first proposed in 2016. The refinements narrowed the mass estimate. They narrowed the orbital range. They incorporated new data from distant icy bodies whose paths through space behave as though something heavy is pulling on them. 4.4 Earth masses is small for a planet by outer solar system standards. Neptune is 17 Earth masses. Uranus is 14.5. But 4.4 Earth masses is large enough to dominate the gravitational environment of the outer solar system, large enough to sculpt orbits, large enough to tilt and twist them into patterns that should not exist without a cause. The evidence is indirect, entirely indirect. Every piece of it comes from watching other objects and measuring how they move. This is gravitational inference, the same method that led to the discovery of Neptune in 1846. Astronomers noticed that Uranus was not where it should be. They calculated where an unseen planet would need to sit to produce the observed deviations. They pointed a telescope at that spot. Neptune was there. The Planet 9 hypothesis follows the same logic. Distant objects beyond Neptune cluster in ways that probability alone cannot explain. Their orbits share orientations. Their tilts align. The simplest explanation for these alignments is a single massive body orbiting far from the central star. It would slowly herd everything around it into formation. The Caltech team has spent years building this case. Konstantin Batygin, a theoretical astrophysicist, handles the orbital mechanics. Mike Brown, an observational astronomer, handles the search. Together, they have published multiple papers refining the predicted mass, orbit, and sky location of this unseen world. And the scientific community is listening. Survey telescopes are dedicating observation time to the search. The Vera Rubin Observatory in Chile, scheduled for full operations, will scan the southern sky with enough depth and cadence to to spot a planet at 400 astronomical units. If it is there, the history of Planet X, the hypothetical planet beyond Neptune, stretches back more than a century. It is a history littered with false starts, miscalculations, and one spectacular coincidence that confused the entire field for 76 years. The current hypothesis is built on better data and better math than any previous version. But better does not mean certain. This is the story of that search. The mistakes and the arguments and the evidence that keeps accumulating despite every effort to explain it away. Percival Lowell was born in 1855 to one of the wealthiest families in Boston. His brother, Abbott Lawrence Lowell, became president of Harvard. His sister Amy became a poet who won the Pulitzer Prize posthumously. Lowell became obsessed with Mars. In 1894, he built an observatory in Flagstaff, Arizona, at an elevation of over 7,000 feet, specifically to study the red planet. He was convinced that the dark lines Giovanni Schiaparelli had observed on the Martian surface were canals, engineered waterways, evidence of an intelligent civilization struggling to irrigate a dying world. He wrote 3 books about it. He gave public lectures that filled auditoriums. He drew elaborate maps of the canal networks, complete with intersection points he called oases. The scientific community was skeptical. Other astronomers with comparable telescopes could not see the canals. Some suspected the lines were optical illusions created by the human eye's tendency to connect discrete features into continuous patterns. Edward Barnard at the Lick Observatory, working with a larger telescope in better seeing conditions, he saw no canals at all. Lowell did not care. He was wealthy enough to fund his own research and famous enough to command public attention. He was also stubborn enough to ignore his critics entirely. By 1906, he had moved on to a new obsession. The orbit of Uranus contained irregularities that the gravitational influence of Neptune alone could not fully explain. Lowell believed these residual perturbations pointed to another planet, a massive one, roughly 7 Earth masses, orbiting far beyond Neptune in the cold darkness of the outer solar system. He called it Planet X. The X stood for unknown. Lowell spent the last decade of his life calculating where Planet X should be. He used the observed deviations in the orbit of Uranus to work backward and estimated the mass and position of the hypothetical body. The mathematics was laborious. Every calculation had to be done by hand or with mechanical computing devices. He employed a team of human computers, mostly women, to perform the repetitive arithmetic. He published his predictions in 1915. Planet X, according to Lowell, should sit in the constellation Gemini, with a mass comparable to Neptune. It should be findable with a sufficiently powerful telescope and a systematic photographic survey of the sky. Lowell died on November 12, 1916. He was 61. He never found Planet X. He never abandoned the idea of Martian canals either. He left behind an observatory, a fortune, and a set of predictions that his colleagues felt obligated to test. The Lowell Observatory continued the search after his death. It was sporadic at first. Legal disputes over Lowell's estate consumed resources and attention for years. His widow Constance contested the will. The observatory's funding was uncertain, but the staff kept looking. They photographed sections of the sky near Lowell's predicted position. They compared plates taken weeks apart and looked for any point of light that moved against the background stars. A moving dot would mean a nearby object. A nearby object in roughly the right position would mean Lowell was right. The search dragged on through the 1920s with no result. By that point, most professional astronomers had lost interest. The perturbations in the orbit of Uranus were small. The predicted planet was far away and presumably faint. And Lowell's reputation, tarnished by the canal debacle, made the entire enterprise feel slightly disreputable. The observatory needed a breakthrough. What it got instead was a 24-year-old from Kansas with no college degree and a homemade telescope. Clyde Tombaugh arrived at the Lowell Observatory in January of 1929. He was a farm boy from Burdett, Kansas, population roughly 400. He had built his own reflecting telescope out of parts from a 1910 Buick and a cream separator. He used it to sketch Jupiter and Mars from his family's wheat field on clear nights after long days of farm work. He mailed the drawings to the Lowell Observatory and hoped for feedback. They offered him a job. Tombaugh was 22 years old. He had never attended college. His assignment was simple and brutal. Photograph the sky along the ecliptic, the plane where planets orbit. Compare each pair of photographic plates using a blink comparator, a device that rapidly alternates between two images of the same star field taken days apart. Any object that shifts position between exposures belongs to the solar system. Everything else is a distant star, fixed in place. Tombaugh was methodical. He worked long hours at the telescope, then spent even longer hours at the blink comparator and scanned each plate pair for movement. The plates contained hundreds of thousands of stars. Most nights produced nothing. On February 18, 1930, Tombaugh found it. A tiny dot that shifted position between plates taken on January 23rd and January 29th. The object was near the constellation Gemini. It was close to where Lowell had predicted Planet X would be. The Lowell Observatory announced the discovery on March 13, 1930. The date was chosen deliberately. It was the anniversary of both Lowell's birth and the discovery of Uranus by William Herschel. They named the new object Pluto. The name was suggested by an 11-year-old girl in Oxford, England, named Venetia Burney. She thought the god of the underworld suited a cold, dark, distant world. The first two letters, P and L, also served as Percival Lowell's initials. The observatory adopted the name within weeks. The celebration was enormous. Newspapers ran front-page stories. Lowell's prediction, it seemed, had been vindicated. Planet X had been found. Lowell was right all along. There was a problem. Pluto was tiny. Initial estimates placed its mass at roughly 1 Earth mass. That was already suspiciously small for a planet supposedly tugging on Uranus. Over the following decades, the estimate kept shrinking. By the 1950s, it was down to 1/10 of an Earth mass. By the 1970s, closer to 1/100th. In 1978, James Christie at the United States Naval Observatory discovered that Pluto had a moon. He named it Charon. The moon's orbit allowed a precise calculation of Pluto's mass. The answer was 0.002 Earth masses. That is roughly 3,500 times too small to produce the gravitational perturbations Lowell had attributed to Planet X. Pluto was found within 6 degrees of Lowell's predicted position. This looked like confirmation. It was coincidence. Lowell's calculations were based on orbital residuals that, as later analysis showed, were largely the product of measurement error. He predicted a 7 Earth mass planet. He got a body smaller than Earth's moon. The proximity was pure chance. The astronomical community knew this relatively early. By the 1940s, it was clear that Pluto was far too small. But the public celebration had already cemented Pluto's status. Textbooks listed 9 planets. School children memorized the mnemonic, and for 76 years, the question of whether a real massive planet lurked beyond Neptune was buried under the assumption that Tombaugh had already answered it. In August of 1989, Voyager 2 flew past Neptune. The spacecraft had launched 12 years earlier from Cape Canaveral and had already visited Jupiter, Saturn, and Uranus on a grand tour made possible by a rare planetary alignment that occurs once every 175 years. Neptune was its final target. Voyager 2 passed within 3,000 miles of Neptune's cloud tops on August 25th. It measured the planet's magnetic field. It photographed its largest moon, Triton. The images revealed geysers of nitrogen ice erupting from the surface into thin plumes that stretched 5 miles high. It discovered 6 previously unknown moons and found rings where none had been confirmed, and it produced a precise measurement of Neptune's mass. That measurement changed everything. Before Voyager 2, Neptune's mass was known only from ground-based observations of its gravitational effect on other bodies. Those observations carried a margin of error, a small one by astronomical standards, roughly 0.5%. 0.5% sounds trivial. For most purposes, it is. It was enough to create a phantom. The entire case for Planet X, going all the way back to Percival Lowell, rested on irregularities in the orbit of Uranus. Uranus was not moving exactly as predicted by Newton's laws. After accounting for the known positions and masses of the other planets, the gap between prediction and observation was small. Lowell attributed that gap to an undiscovered planet that pulled on Uranus from beyond Neptune. Voyager 2's precise mass measurement of Neptune eliminated the gap entirely. When scientists plugged the corrected mass into their orbital models, the predicted path of Uranus matched its observed path perfectly. There were no residual perturbations. There was no anomalous tug. There was no need for Planet X. Miles Standish at NASA's Jet Propulsion Laboratory published the definitive analysis in 1993. He recalculated the orbits of the outer planets using the updated Neptunian mass from Voyager 2's flyby data. Every supposed anomaly in the motion of Uranus vanished. The century-long search for Planet X had been chasing a measurement error. The original sin was precision, or rather, a lack of it. 19th century astronomers measured Neptune's position against background stars using visual observations through telescopes. Those measurements were good. They were not good enough. A 0.5% error in the mass of a planet 17 times heavier than Earth translates to a significant gravitational miscalculation when projected across decades of orbital motion. The error compounded with time and grew larger the further forward or backward the predictions extended. Lowell built his entire prediction on that miscalculation. Tombaugh found Pluto in roughly the right spot by accident, and the astronomical community spent 7 decades treating the coincidence as confirmation. Voyager 2 ended it. After 1989, there was no observational reason to believe a massive planet existed beyond Neptune. The perturbations were gone. The math balanced. Planet X was dead. Textbooks did not update immediately. Public awareness lagged even further. Pluto remained the 9th planet in the popular imagination for another 17 years. But within the professional community, the question was settled. The outer solar system contained 4 giant planets, a scattering of icy debris, and Pluto, which was clearly something other than what Lowell had predicted. No one was actively looking for a new planet anymore. The search had consumed nearly a century of effort and produced exactly one discovery, Pluto, which turned out to be the wrong answer to the wrong question. The case was closed, the file was archived, and for about 14 years, nobody reopened it. On November 14, 2003, Mike Brown, Chad Trujillo, and David Rabinowitz announced the discovery of an object they would eventually name Sedna. Brown was a professor of planetary astronomy at Caltech. Trujillo was a former student of his, then at the Gemini Observatory in Hawaii. Rabinowitz was at Yale. They found Sedna using the Samuel Oschin telescope at Palomar Observatory in Southern California, a 48-inch wide field survey instrument that had been photographing the sky since 1948. Sedna was roughly 620 miles in diameter, about 1/3 the size of Pluto. In terms of mass, it was ordinary, another chunk of ice and rock in the outer solar system. Its orbit was the problem. Sedna's closest approach to the central star, its perihelion, was 76 astronomical units. Neptune orbits at 30. Pluto's perihelion is at about 29. Sedna never comes anywhere near Neptune. Its farthest point from our star, its aphelion, was roughly 937 astronomical units. The orbital period was approximately 11,400 years. That meant Sedna had last been at its closest point to the inner solar system around 9,400 BCE, before agriculture, before writing, before the wheel. The orbit itself was elongated and tilted relative to the plane where the major planets travel. This combination created a classification problem that no one had encountered before. Sedna was too far from Neptune to have been scattered outward by a gravitational encounter. Objects that Neptune has kicked into distant orbits still pass through Neptune's neighborhood on each trip around the star. Sedna does not. It was too close to have originated in the Oort cloud, the theoretical shell of icy objects at 20,000 to 100,000 astronomical units that is thought to be the source of long-period comets. And it was too eccentric to belong to the classical Kuiper belt, whose members orbit in relatively circular paths between 30 and 50 astronomical units. Sedna occupied a gravitational desert, a region of space where no known mechanism could have placed it. Brown called it the most scientifically important trans-Neptunian object found to date. Every previous discovery in the outer solar system could be explained by the gravitational influence of the 8 known planets. Sedna could not. The question was immediate. How did Sedna get there? Several hypotheses circulated. A passing star in the early history of the solar system might have tugged Sedna into its current orbit during a close flyby. The gravitational influence of other stars in the birth cluster where Sol formed could have done it. Those stars would have pulled on the young solar system's outermost debris before the cluster dispersed. Or something massive, something still out there, could be maintaining Sedna's orbit through ongoing gravitational interaction. Each hypothesis had problems. The passing star scenario required a very specific encounter geometry. Too close, and it would have disrupted the entire outer solar system. Too far, and it would not have affected Sedna enough. The birth cluster hypothesis was plausible, but hard to test, because the cluster dispersed billions of years ago. The single object problem limited what scientists could conclude. One unusual orbit could be explained by many things. A fluke encounter billions of years ago. A rare dynamical pathway. With only one example, there was no way to distinguish between explanations. Brown and Trujillo knew they needed more objects like Sedna. They needed to determine whether Sedna was unique or representative of a hidden population. If other bodies shared similar orbits, the pattern might point toward a cause. They kept searching. In 2014, Chad Trujillo and Scott Shepard of the Carnegie Institution for Science announced they had found a second object with an orbit resembling Sedna's. They designated it 2012 VP-113. Its perihelion was 80.5 astronomical units, even farther from the central star than Sedna's closest approach. Its semi-major axis placed it deep in the same gravitational desert where nothing should be. Two objects with similar orbits was interesting. What Trujillo and Shepard noticed next was more than interesting. They plotted the orbital parameters of 2012 VP-113 alongside Sedna and 4 other extreme trans-Neptunian objects. These were bodies with semi-major axes greater than 150 astronomical units and perihelia beyond Neptune's orbit. 6 objects in total. All 6 shared a peculiar property. Their arguments of perihelion, a technical parameter describing the orientation of the closest approach point relative to the orbital plane, clustered near 0 degrees. In a solar system with no hidden influences, these values should be randomly distributed. They should scatter evenly around 360 degrees. Instead, all 6 objects had arguments of perihelion in the same narrow range. Trujillo and Shepard calculated the probability of this alignment occurring by chance, 0.007%, roughly 1 in 14,000. That number assumed the sample was unbiased. It assumed the 6 objects had been discovered through surveys that could have found them anywhere in their orbits, in any orientation. If true, the clustering demanded an explanation. Trujillo and Shepard proposed one. A massive planet, orbiting far beyond Neptune, could be acting as a gravitational shepherd. Its gravity would slowly torque the orbits of smaller objects. Over millions of years, it would push their arguments of perihelion towards similar values. The planet would need to be large. Several Earth masses at minimum. It would need to orbit at hundreds of astronomical units and to have been there for billions of years, slowly sculpting the orbits of everything in its vicinity into a common alignment. The paper landed in the journal Nature in 2014. The response from the community was cautious. 6 objects was a small sample. The surveys that found them covered limited portions of the sky. The statistical significance depended entirely on whether the sample was representative of the true population. Several researchers pointed out that small number statistics can produce patterns that vanish when more data arrives. Apparent clustering in a handful of objects does not necessarily reflect real clustering in the underlying population. Others noted that the orbital clustering might reflect where telescopes had looked rather than where objects actually were. If surveys preferentially covered certain parts of the sky, the objects found would naturally cluster in those directions, regardless of the true distribution. But the pattern was there. 6 bodies spread across billions of miles of space, discovered by different teams using different telescopes at different times, all sharing an orbital alignment that probability said should almost never happen by accident. The objects had been found over a span of more than a decade, different observatories in different hemispheres, different instruments with different sensitivities, and yet all 6 pointed the same way. Trujillo and Shepard were careful in their language. They presented the data and proposed the planet hypothesis as one possible explanation. They called for more observations and more careful characterization of survey biases. 2 researchers at Caltech were already paying close attention. Mike Brown's Twitter handle was @PlutoKiller. He had earned it. In 2005, Brown and his team discovered Eris, an object in the scattered disk beyond Neptune. Eris was roughly the same size as Pluto, possibly larger. Its discovery forced a question the International Astronomical Union had been avoiding for years. If Pluto was a planet, was Eris also a planet? What about the other large objects Brown kept finding? Make, discovered in 2005. Haumea, identified the same year. The Kuiper Belt was filling up with Pluto-sized bodies. Either the solar system had 12 or 15 planets, or Pluto needed to be reclassified. The International Astronomical Union voted in August of 2006. They created a new category, dwarf planet, and placed Pluto in it alongside Eris and Ceres. Pluto was no longer the 9th planet. Brown had forced the demotion. He wrote a book about it called How I Killed Pluto and Why It Had It Coming. He was not apologetic. He argued that Pluto had never fit the definition of a planet in any meaningful scientific sense. It was one of thousands of icy objects orbiting in the Kuiper Belt. Calling it a planet was sentimental, historically contingent, and scientifically misleading. The public did not entirely agree. Brown received hate mail. Schoolchildren wrote him angry letters. He leaned into it. The @PlutoKiller handle stayed. Konstantin Batygin was a different kind of scientist, a theorist. Born in Moscow in 1986, raised partly in Japan, educated at the University of California, Santa Cruz, he arrived at Caltech as a postdoctoral researcher and stayed. His specialty was orbital dynamics, the mathematics of how bodies move under gravitational influence over deep time. He built models of how planetary systems evolve across millions and billions of years. In 2016, Brown and Batygin published a paper in the Astronomical Journal. It was titled Evidence for a Distant Giant Planet in the Solar System. The paper proposed that a planet with a mass between 5 and 10 times that of Earth was orbiting the host star at a distance of 400 to 800 astronomical units. The orbital period would be 10,000 to 20,000 years. The paper was rigorous. It went beyond the 6-object clustering that Trujillo and Shepard had identified. Brown and Batygin showed that the same hypothetical planet could explain multiple features of the outer solar system simultaneously. The clustering of orbital orientations, the existence of objects with orbits perpendicular to the plane of the major planets, the slight tilt of the planetary plane relative to the star's equator, one planet, multiple explanations. The man who had killed the ninth planet was now proposing a replacement, a real ninth planet, massive enough to dominate the outer solar system, too far away and too faint to have been spotted by any existing survey. Brown had spent a decade arguing that Pluto was never a true planet. Now, he was claiming to have found evidence for something that genuinely was. The paper accumulated over 1,500 citations within its first few years. It became one of the most discussed results in planetary science in decades. Observatories around the world began allocating telescope time to search the predicted region of sky. The race to find Planet 9 had started. The strength of the Batygin and Brown model lay in its predictions. A good scientific hypothesis does more than explain existing data. It tells you what else you should find if the hypothesis is correct. It risks being wrong in specific, testable ways. Planet 9, as the media quickly named it, made specific predictions. The first prediction concerned perpendicular orbits. The model showed that a massive planet at several hundred astronomical units would gradually torque some trans-Neptunian objects into orbits tilted roughly 90 degrees relative to the plane where the 8 known planets travel. These perpendicular objects should exist if Planet 9 exists. They did exist. 5 trans-Neptunian objects with nearly perpendicular orbits had already been discovered before the 2016 paper was published. No one had an explanation for them. The Planet 9 model provided one without being tuned to fit. The perpendicular orbits fell out of the mathematics naturally. Batygin and Brown had not designed their model to produce this result. They were simulating the long-term evolution of trans-Neptunian orbits in the presence of a distant massive body. The perpendicular population appeared on its own. It was an emergent property of the gravitational dynamics. When they checked the astronomical catalogues, the predicted objects were already there. The second prediction was subtler. The model predicted that the gravitational influence of Planet 9 would tilt the orbital plane of the 8 known planets relative to the spin axis of the host star. The tilt should be approximately 6 degrees. Astronomers had known for decades that the orbital plane of the planets is tilted about 6 degrees relative to the star's equator. This tilt had no accepted explanation. The star formed from a spinning disk of gas and dust. The planets formed from that same disk. They should share the same plane. They do not. Planet 9 offered a reason. A distant massive body on an inclined orbit would slowly precess the entire inner planetary system. Over billions of years, the plane would tilt away from the star's spin axis. 6 degrees was exactly what the model produced. The match was not forced. Batygin and Brown did not adjust their planet's parameters to generate this number. It emerged from the same model that explained the orbital clustering. This kind of result carries real weight in physics. A single hypothesis that independently resolves multiple unrelated puzzles is rare. Each puzzle it solves without being specifically adjusted to solve increases confidence that the hypothesis reflects something real. The orbital clustering of extreme trans-Neptunian objects, the existence of perpendicular orbits, the 6-degree obliquity of our star's spin axis, the detachment of bodies like Sedna, 4 separate mysteries. Planet 9 connected them. The model also made predictions that had not yet been tested. It specified a region of sky where the planet should be located. It constrained the brightness the planet should have at various wavelengths. It described the orbital characteristics of additional trans-Neptunian objects that should be discovered if future surveys looked in the right places. These untested predictions gave the hypothesis something Lowell's prediction had lacked: falsifiability with real teeth. If the Vera Rubin Observatory completed its 10-year survey and found no planet in the predicted mass and orbital range, the hypothesis would be in serious trouble. Batygin and Brown accepted this. They welcomed it. A hypothesis that cannot be killed by data is not science. Planet 9 could be killed by data. That was precisely what made it worth testing. Samantha Lawler did not think the evidence held up. Lawler was an astronomer at the University of Victoria in British Columbia. She worked on the Outer Solar System Origins Survey, known by its acronym OSOS. The survey used the Canada-France-Hawaii telescope on Mauna Kea to systematically map trans-Neptunian objects. It was designed from the start to account for observational bias. That term, observational bias, was the core of Lawler's argument against Planet 9. Telescopes do not see everything. They see what they can see, given their location, their field of view, the time of year, the brightness limits of their instruments, and the portion of sky their operators choose to observe. Objects discovered in surveys reflect both the real population and the survey's blind spots. An object sitting in a part of the sky your telescope never pointed at might as well not exist. In 2017, Lawler and her colleagues published an analysis. They examined whether the orbital clustering that Trujillo, Shepard, Batygin, and Brown had identified could be an artifact of where astronomers had pointed their telescopes. The answer, according to OSSOS, was yes. The survey team built detailed simulations. They modeled what a uniform, unclustered population of trans-Neptunian objects would look like if observed through the specific telescopes and survey strategies that had actually been used. The simulations produced apparent clustering. Objects seemed to bunch together in certain orbital orientations, even though the underlying population was evenly distributed. The bunching was a shadow of the survey geometry projected onto the data. Lawler's team argued that the 0.007% probability Trujillo and Shepard had calculated was meaningless. That number assumed unbiased detection. If the detections were biased, and they almost certainly were to some degree, the probability calculation was built on a false premise. The impressive-looking statistic was an artifact of incomplete accounting. OSSOS had characterized its own biases exhaustively. Every pointing and every exposure time was recorded and published alongside the data, along with every detection limit. When the team analyzed only the objects discovered by OSOS and applied their own bias corrections, the clustering signal disappeared. The objects were consistent with a uniform distribution, no Shepard needed. The argument cut deep. It did not disprove Planet 9's existence. It attacked the statistical foundation on which the hypothesis rested. If the clustering was an artifact, the primary line of evidence evaporated. Batygin and Brown pushed back. They argued that OSOS had discovered too few extreme trans-Neptunian objects to draw conclusions about clustering. The OSOS sample included only a handful of objects in the relevant orbital range. Small samples are compatible with almost any underlying distribution. They also pointed out that the OSOS analysis focused narrowly on the clustering evidence, while ignoring the perpendicular orbits and the 6-degree obliquity prediction. Those features were independent of survey bias. They existed regardless of where telescopes had looked. The debate became one of the more contentious in planetary science. Both sides published detailed rebuttals. Conferences featured dueling presentations. Graduate students learned to identify which camp their advisors belonged to before choosing thesis topics. The field had split, and the split was not purely academic. Telescope time is a finite resource. Every hour spent searching for Planet 9 is an hour not spent on other science. If the planet was real, the search was justified. If it was a statistical mirage, the community was wasting precious, observing time chasing a ghost. The stakes extended beyond any single career or publication. On October 1st, 2018, Scott Shepard and his collaborators announced the discovery of 2015 TG387. They called it the Goblin. The nickname came from the TG in its designation and the fact that it was announced near Halloween. It stuck. The goblin was small, roughly 200 miles across, another ice and rock fragment drifting through the deep outer solar system. Nothing special in size. Its orbit was anything but perihelion at 65 astronomical units, well beyond Neptune's gravitational reach. Semi-major axis at roughly 1,170 astronomical units. Orbital period approximately 40,000 years. The last time the goblin was at its closest point to our star, modern humans were painting on cave walls in southern Europe and crossing land bridges into new continents. Shepard's team ran dynamical simulations. They tested whether the goblin's orbit was stable in a solar system with and without Planet 9. The results were clear. Without Planet 9, the orbit was unstable over billions of years. Gravitational interactions with the known giant planets would eventually eject the goblin or alter its path beyond recognition. The orbit unraveled, with Planet 9 included in the simulation and the mass and orbital parameters from the Batygin and Brown model. The goblin's orbit remained stable for the full age of the solar system. 4.5 billion years. The planet acted as a shepherd. Its gravitational influence nudged the goblin at regular intervals. It maintained the elongated path through a mechanism called mean motion resonance. Each time the goblin completed one orbit, Planet 9 had completed a specific whole number ratio of its own. The timing kept the two bodies from ever passing close enough for a disruptive encounter. The goblin also fit the clustering pattern. Its argument of perihelion aligned with the other extreme trans-Neptunian objects, and it was found in a part of the sky that the OSSOS bias analysis had limited ability to address. Lawler's team had characterized the biases of specific surveys. The goblin was discovered by a different survey using a different telescope with different sky coverage and different observing seasons. Each new object discovered by an independent survey made the bias explanation harder to sustain. The argument required that every survey, conducted by different teams with different instruments pointing at different parts of the sky at different times of year, happened to share the same systematic bias. Possible in principle, increasingly difficult to defend with each new data point. Shepard emphasized this in the discovery paper. The goblin was the third object, after Sedna and 2012 VP 113, with a perihelion far beyond Neptune and an orbit consistent with Planet 9 shepherding. 3 objects from 3 different surveys, using 3 different telescopes. Brown and Batygin updated their orbital model to incorporate the goblin and other recent discoveries. The updated model narrowed the predicted mass and orbit of Planet 9. Each new extreme trans-Neptunian object added a constraint. Each constraint shrank the region of parameter space where the planet could hide. The goblin did not prove Planet 9 existed. Proof would require a direct detection, a photograph, a spectrum, a confirmed point of light at the predicted position, moving at the predicted rate. But the goblin added weight. It was another data point that behaved exactly as the model predicted. Another object whose orbit made more sense in a solar system with 9 planets than in one with 8. In 1983, NASA strapped an infrared telescope to a satellite and launched it into polar orbit. The mission was called IRAS, the Infrared Astronomical Satellite. It was the first instrument to survey the entire sky in infrared light, and it operated for just 10 months. Then its liquid helium coolant boiled away and the detectors went warm and blind. In that brief window, IRAS catalogued roughly 350,000 discrete infrared sources: stars, galaxies, dust clouds, asteroids, faint smears of unknown origin. The data was archived and made public. Scientists picked through the catalog for decades and mined it for brown dwarfs and distant galaxies and young stellar objects. Nobody was looking for a planet. 42 years later, a researcher named Terry Long Phan did something that sounds almost too simple to be real. He took the IRAS catalog and cross-referenced it against data from AK, a Japanese infrared satellite that performed its own all-sky survey in 2006. 2 missions, 2 epochs, 23 years apart. If something in the IRAS data had moved between 1983 and 2006, it would appear at slightly different coordinates in the 2 catalogs. A star would not move. A galaxy would not move. A planet would. Phan started with roughly 2 million sources. He applied filters for brightness, for color temperature, for positional uncertainty. The list shrank. 2 million became a few thousand. A few thousand became a few hundred. A few hundred became 13. 13 objects that appeared in both catalogs at positions consistent with slow, steady motion across the sky. 13 candidates that might be the same object seen 23 years apart. Of those 13, one stood out. It had moved approximately 47 arc minutes between the 2 surveys. That is a small angle, less than the apparent width of a full moon. But for an object in the outer solar system, it is exactly the kind of motion you would expect. Slow, deliberate, consistent with something orbiting Sol. At enormous distance, the implications landed hard. If Phan's candidate is real, then Planet 9 was photographed in 1983. It was sitting in a public database the entire time. 4 decades of searching, of modeling, of arguing over orbital parameters and statistical significance, and the evidence may have been archived on magnetic tape in a government data center since the Reagan administration. There are caveats. IRAS had low spatial resolution by modern standards. The pixels were fat. The positional uncertainties are large, sometimes spanning several arc minutes in a single measurement. The candidate could be 2 entirely unrelated sources that happen to fall near each other on the sky when viewed across a 23-year baseline. Infrared catalogs are crowded places. Faint sources blend together. Instrumental artifacts masquerade as real objects. A single coincidence does not constitute a detection. Confirmation requires follow-up observations at the predicted current position. If the object is real and has continued on the same trajectory, it should now be located at a specific set of coordinates that can be calculated from the 2 earlier measurements. Point a modern infrared telescope at that spot. If something is there, the cold case is solved. That work is ongoing, but the possibility alone shifted the conversation. It suggested that the hunt for Planet 9 had been a cold case all along. The photograph existed, the evidence was collected and archived and indexed, and made freely available to anyone with an internet connection. It just needed someone to open the file and look. And for 41 years, nobody did. The planet that Konstantin Batygin and Mike Brown described in 2016 was supposed to be a super-Earth, something between 5 and 10 times the mass of our own world. Rocky, perhaps, or wrapped in a modest envelope of hydrogen and helium, dense enough to sculpt the orbits of distant icy bodies, small enough to have escaped detection for the entire history of telescopic astronomy. The mass estimate of 4.4 Earth masses, published in 2025, seemed to confirm this picture. A middleweight planet, larger than Earth, smaller than Neptune, hiding in the dark. Terry Long Phan's IRAS candidate complicated everything. The problem was brightness. If the candidate source in the IRAS data is genuinely a planet at the predicted distance, then its infrared emission implies something larger than a super-Earth, significantly larger. The thermal signature is more consistent with a body in the mass range of Uranus or Neptune, a gas giant, or at minimum, an ice giant with a thick atmosphere of hydrogen, helium, methane, and ammonia. This mattered for several reasons. A super-Earth at 500 astronomical units could plausibly have formed in the inner solar system and been ejected outward through gravitational interactions with Jupiter or Saturn during the chaotic early period of planetary migration. The physics works. The timescales are reasonable, models reproduce it reliably. An ice giant is harder to explain. Uranus and Neptune themselves barely had enough time to form where they currently orbit, roughly 19 and 30 astronomical units from the central star. The outer solar system was too sparse, too cold, too thinly spread with raw material for giant planet cores to assemble quickly. Moving that formation problem to 500 astronomical units makes it worse by orders of magnitude. There is simply no mechanism in standard core accretion theory that produces a Neptune-mass planet at that distance. The alternative is that it formed closer in and was scattered outward, the same story proposed for the super-Earth version. But scattering a larger planet requires a more violent encounter. The energy budget changes, the probability drops, and the orbital outcome is harder to reconcile with the relatively stable, roughly circular orbit that the clustering of trans-Neptunian objects seems to demand. Then there is the question of detection. Astronomers have been searching for Planet 9 with some of the most powerful survey instruments ever built. If the object is a super-Earth, its faintness makes sense. A rocky body 5 times the mass of Earth at 500 astronomical units would reflect almost no light from the host star and emit very little infrared radiation of its own. It would be extraordinarily dim, nearly invisible, but a Neptune-class body would be brighter, larger surface area, more atmospheric gas to reflect starlight, more internal heat to radiate. The fact that such an object has evaded detection for this long raises uncomfortable questions. Either the orbital predictions are slightly off and the search is pointed at the wrong patch of sky, or the planet is embedded in a region of the Milky Way's galactic plane where background stars are so dense that it disappears into the crowd, or the surveys have not gone deep enough in the right wavelengths. Each answer carries its own consequences. The search is no longer just about finding a planet. It is about figuring out what kind of planet could exist where no planet has any right to be. In 2019, 2 physicists at Durham University published a paper that proposed something genuinely strange. Jakub Skoltz and James Unwin suggested that the gravitational anomalies in the outer solar system might be caused by a primordial black hole. The idea requires some context. Black holes come in different sizes. The ones that form from collapsing stars are typically several times the mass of Sol. The supermassive ones at the centers of galaxies weigh millions or billions of times more. But theoretical physics allows for a third category. In the first fraction of a second after the Big Bang, when the universe was unimaginably dense and hot, random fluctuations in the distribution of matter could have compressed small regions past their Schwarzschild radius. These regions would have collapsed into black holes immediately. Not stellar mass, not supermassive, tiny, primordial. A primordial black hole with the mass of 5 Earths would be roughly 4 inches across. About the size of a tennis ball, it would warp space and time with the same gravitational authority as a rocky or icy planet of identical mass. Every trans-Neptunian object that Planet 9 supposedly shepherds would behave exactly the same way in the presence of this black hole. The orbits would cluster. Sedna would still make sense. The goblin would still fit. From a gravitational perspective, the 2 explanations are indistinguishable, but a primordial black hole would be invisible. It emits no light. It reflects no light. It has no atmosphere to scatter photons and no surface to radiate heat. Every telescope ever pointed at the outer solar system would see nothing. Infrared surveys would find nothing. Optical surveys would find nothing. The object would be gravitationally present and electromagnetically absent. Scholz and Unwin knew this made their hypothesis difficult to test. They proposed it partly as a thought experiment, a way of illustrating that the gravitational evidence for Planet 9 does not uniquely point to a planet. It points to mass. The nature of that mass remains open. A year later, Amir Siraj and Avi Loeb at Harvard offered a way to look. They argued that a primordial black hole drifting through the outer solar system would occasionally encounter small bodies, comets, and asteroids, chunks of ice on long, lonely orbits. When one of these objects strayed close enough, the black hole's tidal forces would tear it apart. The debris would spiral inward and heat to extreme temperatures on its way toward the event horizon. For a brief moment, the impact would produce a flare of radiation, a flash visible in the right wavelength. Blink and you miss it, but with a wide-field survey telescope monitoring the sky continuously, you might catch one. The detection rate would be low, perhaps a handful of flares per year. The rate would depend on the density of small bodies in the neighborhood. Each flare would last hours, maybe days. The signal would be faint, but it would be there, and its location would trace the orbit of the invisible object producing it. Nobody has detected such a flare. The technology to search systematically is only now coming online. The hypothesis remains exactly that, a hypothesis. But it lives in the literature as a reminder that the outer solar system may contain things that do not fit neatly into the category of planet. In 2023, a team of researchers proposed that the entire Planet 9 hypothesis might be unnecessary. Their argument did not involve a black hole or a hidden planet or any unseen object at all. It involved gravity itself. The framework is called Modified Newtonian Dynamics, MOND. It was originally proposed in 1983 by the Israeli physicist Mordechai Milgrom as an alternative to dark matter. Milgrom noticed that the rotation curves of galaxies, the way stars orbit their galactic centers at speeds that seem too fast to be explained by visible mass alone, could be accounted for by modifying Newton's law of gravitation at very low accelerations. Below a certain threshold, gravity would behave slightly differently than Newton predicted: stronger, stickier, enough to hold galaxies together without invoking invisible matter. MOND has spent 4 decades on the fringes of mainstream physics. It works well for galaxies, better than it should. It fails for galaxy clusters. It lacks a complete relativistic formulation, though attempts exist. Most physicists regard it as interesting, occasionally useful, and probably wrong. Dark matter remains the dominant paradigm, but the 2023 paper applied MOND to the outer solar system. At distances of several hundred astronomical units from Sol, the gravitational acceleration drops to values near Milgrom's threshold. The authors showed that in this regime, the galactic tidal field, the gentle gravitational pull of the Milky Way itself, could produce an alignment effect on the orbits of distant trans-Neptunian objects. The clustering that Batygin and Brown attributed to a hidden planet could emerge naturally from the interaction between a modified gravity law and the galaxy's own gravitational influence. No planet required, no black hole, no additional mass of any kind, just a different equation for how gravity works when it gets very, very weak. The stakes of this argument are difficult to overstate. If MOND correctly explains the orbital clustering in the outer solar system, then Isaac Newton's law of universal gravitation is incomplete. It works beautifully for apples and cannonballs and the orbit of the Moon. It works for Mercury and Mars and the trajectory of every spacecraft ever launched. But at the farthest edges of the star's gravitational domain, where acceleration drops below a billionth of what you feel standing on Earth's surface, the law breaks. This would be a bigger discovery than any planet. It would mean that the fundamental description of gravity used by physics for over 3 centuries needs revision. It would bolster the case for MOND as a serious alternative to dark matter. It would rewrite textbooks. The paper was met with skepticism. MOND advocates saw vindication. Planet 9 supporters saw a mathematical exercise disconnected from the full body of evidence. Critics pointed out that MOND's predictions for the outer solar system are sensitive to assumptions about the galactic tidal field that remain poorly constrained, and the debate about the clustering itself Whether it is real or an artifact of observational bias applies equally to the MOND explanation. If the clustering is not real, MOND does not need to explain it any more than Planet 9 does. The question shifted. It was no longer simply about whether a planet exists beyond Neptune. It was about whether we understand the force that holds the solar system together. Its formal designation is 2017 OF201. Most people who follow the Planet 9 debate know it by its nickname, Ammonite. The object is roughly 430 miles across, a mid-sized trans-Neptunian body, comparable to some of the larger objects in the Kuiper Belt. Its orbital period is approximately 25,000 years. It travels on a long, stretched ellipse that carries it from a perihelion relatively close to Neptune's orbit, out to an aphelion so distant that the host star would appear as little more than a bright point of light. Ammonite would be forgettable, except for one detail. Its orbit is oriented roughly 90 degrees away from the predicted orbital plane of Planet 9. This matters because the entire Planet 9 hypothesis rests on the idea that a massive unseen body gravitationally shepherds distant objects into aligned orbits. The clustering of trans-Neptunian objects, the shared orientation of their orbital planes, the common direction of their closest approach to Sol, these patterns are the evidence. Planet 9 supposedly maintains this alignment by nudging objects that stray too far back into the fold, the way a sheepdog keeps a flock moving in one direction. Ammonite walked off the cliff in the wrong direction, and nobody saw it coming. When its orbit was calculated and published, opponents of the Planet 9 hypothesis seized on it immediately. Here was an object in exactly the population that Planet 9 was supposed to control, with an orbit that flatly contradicted the predicted alignment. If the shepherd exists, how did this particular sheep end up 90 degrees off course? Supporters of the hypothesis responded with several arguments. The gravitational influence of Planet 9 is complex. It does not simply push every object into the same orbit. Simulations show that some fraction of trans-Neptunian objects should be scattered into perpendicular or even retrograde orbits through a process called the Kozai mechanism, a gravitational interaction that trades orbital inclination for eccentricity over long timescales. In this framework, Ammonite is not evidence against Planet 9. It is a predicted byproduct. But predictions made after the fact carry less weight than predictions made before it. The Kozai mechanism was invoked to explain Ammonite only after Ammonite was discovered. Before its detection, the dominant narrative emphasized clustering and alignment. The existence of a significant outlier was not prominently discussed. This is a recurring pattern in the Planet 9 story. The hypothesis is flexible. When new objects fit the predicted alignment, they are cited as supporting evidence. When new objects deviate, the model accommodates them through secondary mechanisms. Flexibility in a scientific model is not inherently bad. Real gravitational systems are complicated, and a planet's influence on distant objects would indeed produce a range of outcomes. But a model that can explain everything risks explaining nothing. Ammonite did not kill the Planet 9 hypothesis. One object cannot do that, but it introduced doubt of a specific and uncomfortable kind. It showed that the outer solar system contains objects that do not behave the way the simplest version of the model predicts, and it handed Planet 9's critics their first piece of hard orbital evidence that the clustering might be less organized than it appears. The sheep was off the path. The question was whether the shepherd never existed, or whether the flock was always wilder than anyone assumed. By 2025, the argument over Planet 9 had calcified into a statistical trench war. Both sides had numbers. Both sides had confidence. And the numbers disagreed violently. Konstantin Batygin and Mike Brown maintained that the probability of the observed trans-Neptunian orbital clustering occurring by random chance was roughly 0.007%, 1 in 14,000. They had updated their analysis multiple times since 2016. They refined the sample, adjusted for known biases, incorporated newly discovered objects. The number held. The clustering was real, they argued, and it required an explanation. The simplest explanation was a planet. On the other side stood the Outer Solar System Origins Survey, OSSSOS, a Canadian-led project that used the Canada-France-Hawaii telescope to conduct a carefully characterized search for trans-Neptunian objects. The OSS team did something that most other surveys had not. They meticulously documented their own observational biases: where they looked, when they looked, how deep they looked, what they could and could not have detected. Their conclusion was damning. When you account for the fact that most surveys preferentially observe certain parts of the sky at certain times of year, the apparent clustering of trans-Neptunian orbits weakens dramatically. The objects appear clustered because we found them in the places we were already looking. Point your telescope at one patch of sky for 1,000 hours and point it at another patch for 10, and you will find more objects in the first patch. That does not mean the objects are clustered. It means your survey is. The disagreement was not about fraud or incompetence. Both groups published in peer-reviewed journals. Both used legitimate statistical methods. The difference lay in how each group handled the question of observational bias, and that question has no universally agreed upon answer when the sample size is as small as it is. Fewer than 25 extreme trans-Neptunian objects were known, 25 data points. In any other field of science, a sample this small would barely justify a preliminary conference presentation, let alone a decade of international debate. But the outer solar system is stingy with its data. Each new object requires years of observation to pin down its orbit with sufficient precision. The discovery rate is glacial, 1 or 2 per year, in a good year. This created a peculiar dynamic. Every single new discovery had the power to shift the statistical balance. A new object that fit the clustering strengthened Batygin and Brown's case. A new object that did not fit weakened it. The field existed in a state of permanent instability, where the next data point could move the needle in either direction. Some astronomers began comparing the situation to a replication crisis. The original result, the clustering, had been published with high confidence, but independent efforts to confirm it produced mixed results. The signal was there if you analyzed the data one way. It vanished if you analyzed it another way, and nobody could agree on which way was correct. The statistics war revealed something uncomfortable about the scientific process. When the data is sparse and the stakes are high, reasonable people using reasonable methods can reach opposite conclusions. The argument was no longer about the outer solar system alone. It was about the limits of statistical inference at the frontier of observation. In 2006, a Brazilian astronomer named Rodrigo Gomes published a quiet paper in the journal IRAS. Gomes worked at the National Observatory in Rio de Janeiro. His specialty was orbital dynamics, the mathematics of how gravitational interactions shape the trajectories of solar system bodies over millions and billions of years. Gomes had been studying the scattered disk, the population of icy objects beyond Neptune that exist on highly elliptical orbits. These objects had been flung outward during the early era of planetary migration, when the giant planets were still settling into their current positions. Most of the scattered disk could be explained by the known planets, but a handful of objects, the ones on the most extreme orbits, resisted explanation. Their perihelia were too high, their orbits too detached. Something had lifted them away from Neptune's gravitational reach. Gomes proposed that a distant, massive planet could account for the anomalies. He estimated it at roughly Neptune's mass, orbiting at approximately 200 astronomical units from the central star. The planet would interact gravitationally with scattered disk objects over millions of years. Over time, it would raise their perihelia and detach their orbits from the influence of the known giant planets. The paper received modest attention, a few citations, a brief mention in review articles, Then it was largely forgotten. 10 years later, Batygin and Brown published their Planet 9 hypothesis to international fanfare. The core idea was almost identical: a massive planet in the distant solar system that shaped the orbits of extreme trans-Neptunian objects through long-term gravitational interaction. The details differed. Batygin and Brown focused on orbital clustering rather than perihelion detachment. Their predicted planet was lighter and farther out. Their mathematical framework was more elaborate, but the conceptual skeleton was the same. Gomes did not receive significant credit. He was occasionally cited in the literature as a precursor, a footnote in the history section, but the narrative that took hold in the popular press and in much of the scientific community was that Batygin and Brown had discovered the possibility of a ninth planet. The earlier work was acknowledged without being centered. This pattern is older than any living astronomer. Percival Lowell predicted a trans-Neptunian planet in the early 1900s using calculations that were later shown to be based on errors in Neptune's mass. He was right about the existence of something out there, wrong about every detail. Clyde Tombaugh found Pluto in 1930 using Lowell's predictions, but Pluto turned out to be far too small to be the object Lowell had predicted. The right answer found for the wrong reasons, the wrong object discovered in the right place. Gomes may have been the inverse: the right reasons, the right general framework. A decade too early, the field was not ready. The data was not dense enough. The statistical tools were not mature enough to make the case with the kind of force that commands attention. Science rewards not just the first person to see something, but the first person to make others see it. Gomes saw it. Batygin and Brown made the world look. History will sort out who deserves what credit. It usually does, eventually, but eventually can take a very long time. The most interesting thing about Terry Long Phan's study is not what he found, it is what his finding reveals about the machinery of scientific progress and the places where that machinery stalls. The IRAS data has been publicly available since 1984. It is archived, it is downloadable, it has been hosted on NASA servers for over 4 decades. Any astronomer with a computer and a basic understanding of infrared catalog analysis could have done what Phan did. The technique he employed, cross-referencing 2 all-sky infrared surveys taken at different epochs to look for objects that changed position, is straightforward. It is the kind of analysis that gets assigned as a graduate student exercise, not because it is trivial, but because the underlying method is well understood and the tools are accessible. Nobody tried. For 41 years, the data sat in the archive. Hundreds of papers were written using IRAS observations. Thousands of astronomers accessed the catalog. The idea that a faint, slowly moving object might be hiding in the source list was not conceptually difficult. It was, in fact, exactly the kind of thing that IRAS was uniquely positioned to detect. An infrared survey does not care whether an object reflects visible light. It sees thermal emission. A cold planet in the outer solar system would glow faintly in the infrared, even if it was utterly invisible to optical telescopes. So why did nobody look? The answer has less to do with technology or methodology and more to do with assumption. In 1989, Voyager 2 flew past Neptune and allowed astronomers to precisely measure the planet's mass. The updated mass resolved the orbital discrepancies that had motivated the search for Planet X since the late 19th century. There was no missing mass. There was no need for an additional planet. The case was closed, and when a case is closed, people stop investigating. The assumption of emptiness settled over the outer solar system like sediment. Textbooks were updated. Funding priorities shifted. The Kuiper Belt was discovered and explored, but the search for a large, distant planet was considered a historical curiosity. Something that Percival Lowell obsessed over. Something that serious modern astronomers had moved beyond. This assumption was never stated as a formal conclusion. Nobody published a paper titled, "There is definitely nothing else out there." It was more subtle than that. It was a collective turning of attention, a shared sense that the interesting questions lay elsewhere, in exoplanets, in dark energy, in the cosmic microwave background. The outer solar system was mapped, catalogued, and mentally filed away. Phan reopened the file by ignoring the assumption. He treated the data as data without the interpretive layer that 4 decades of consensus had laid on top of it. He asked a simple question: did anything move? And the data answered. If his candidate is confirmed, the lesson will be uncomfortable, not because anyone made a mistake, but because the evidence was always there. It was not hidden by distance or faintness or technological limitation. It was hidden by the belief that there was nothing to find. That belief may have cost the field 40 years. On a mountain in northern Chile called Cerro Pachón, at an elevation of roughly 8,800 feet, a telescope is preparing to change the terms of the debate permanently. The Vera Rubin Observatory is named after the American astronomer who provided some of the most compelling observational evidence for dark matter in the 1970s. The telescope houses a primary mirror 27.5 feet across. Its camera is the largest digital camera ever constructed for astronomy, 3.2 billion pixels. A single exposure covers an area of sky roughly 40 times the size of the full moon. The observatory's primary mission is called the Legacy Survey of Space and Time. Beginning in 2026, the telescope will photograph the entire visible southern sky every 3 nights. It will repeat this cycle for 10 years. Every patch of sky, observed hundreds of times. Every object that moves, catalogued. Every faint smudge that shifts position from one exposure to the next, flagged and tracked. This is the instrument that the Planet 9 hypothesis has been waiting for and dreading. The predicted orbital parameters place Planet 9 somewhere in a broad swath of sky. It would move slowly enough to appear nearly stationary over short timescales, but detectably different over months and years. Previous surveys have searched portions of this region without success. But previous surveys had limitations. They covered incomplete areas. They operated for limited durations. They reached certain depth thresholds and no further. Rubin will go deeper and wider and longer than anything before it. Its repeated imaging strategy means that even extremely faint, slow-moving objects will accumulate signal over time. Stack enough exposures and a dim point of light emerges from the noise. The observatory is projected to eliminate roughly 84% of the remaining parameter space where Planet 9 could be hiding. If Planet 9 exists within the range of orbital distances, brightnesses, and sky positions that current models predict, Rubin will find it. This is a mathematical statement about survey depth, coverage area, and detection probability. And if Rubin does not find it, the implications are equally significant. The absence of a detection after a 10-year survey of this scope would not prove that Planet 9 does not exist. It would prove that Planet 9 does not exist where the models say it should. The predicted orbits would need revision. The mass estimates would need revision. And the hypothesis would face a level of observational pressure that no amount of statistical modeling could deflect. Some astronomers have described the Rubin survey as the endgame. That framing might be premature. Science rarely ends this cleanly. But the observatory will impose a deadline on a debate that has drifted for nearly a decade without resolution. The data will arrive. The object will either appear or it will not. The mountain in Chile is ready. The mirror is polished. The camera is installed. The software pipelines that will process terabytes of data every night are being tested and refined. The first light is imminent. After 20 years of argument and inference and simulation, the outer solar system is about to be photographed with a thoroughness that leaves very few places left to hide. There is a version of this story that does not end with 9. Some of the same dynamical models that predict a single hidden planet in the outer solar system also permit a second one. The idea has been explored in various forms since the mid-2010s. If the trans-Neptunian orbital clustering can be explained by one distant massive body, certain refinements of the data suggest that a single planet may not fully account for all the observed features. Specific objects have orbital characteristics that resist explanation, even with Planet 9 included. Their inclinations are too steep, their perihelia are too high or too low. Their orbital periods do not resonate with the predicted planet in the expected way. One proposed solution is a second hidden planet, informally called Planet Y or Planet 10, smaller than Planet 9, perhaps 1 to 2 Earth masses, orbiting closer to Sol, maybe 200 to 300 astronomical units out in a different orbital plane. Its gravitational influence would be subtler. Its effect on the trans-Neptunian population would overlap with Planet 9's influence in some regions and diverge in others. The evidence for Planet Y is thinner than the evidence for Planet 9, which is itself contested. The models that produce a second planet tend to require specific assumptions about the initial conditions of the solar system. Change the starting parameters slightly, and the need for a second body disappears. The statistical case is fragile and depends on a small number of objects whose orbits carry large uncertainties. But the idea persists because of a deeper pattern, a historical one. Every time astronomers have declared the solar system complete, they have been wrong. William Herschel discovered Uranus in 1781, and for a brief period, the solar system had 7 planets, and that seemed like enough. Then Neptune was found in 1846, predicted by mathematics before it was seen through a telescope. Then Pluto in 1930. Then the Kuiper Belt in the 1990s, and revealed thousands of icy bodies that nobody had imagined. Then Eris in 2005, larger than Pluto and farther out and completely unexpected. Each discovery forced a revision. Each revision revealed that the previous map was incomplete. The pattern is so consistent that it has taken on the character of a rule. The solar system is always bigger and stranger and more populated than the current generation of astronomers believes. Planet Y may be speculative. It may prove unnecessary when better data arrives from the Vera Rubin Observatory and future infrared surveys. It may dissolve into the noise the way so many theoretical predictions have before. But its existence in the models is a reminder. The map is not the territory. The catalogue is not the sky. And the assumption that we have found everything worth finding has been wrong every single time it has been tested. The outer solar system is vast. It stretches from Neptune's orbit to the edge of the star's gravitational influence, a sphere roughly 2 light-years in diameter. We have surveyed a fraction of this volume, a thin slice near the ecliptic plane, a few narrow pencil beams in specific directions. The rest is dark and unknown, and possibly full of things we have not yet learned to look for. If Planet 9 is confirmed, the first question will be whether it is alone. History suggests it will not be. The object that should have settled the argument did the opposite. 2017 OF 201, the one they named Ammonite, orbits at roughly 90 degrees to every other extreme trans-Neptunian object in the sample. When the entire case for Planet 9 rests on orbital alignment, a body flying perpendicular to that alignment looks like a problem, and it is. The question is, what kind of problem? Some researchers saw Ammonite as the death blow. If a massive unseen planet were herding these distant objects into a shared orbital plane, then a body at 90 degrees to that plane should not exist. Its presence suggested the clustering was statistical noise, random scatter, the kind of pattern that appears when you squint at a small dataset and want to see order. Others looked at the same orbit and reached the opposite conclusion. Simulations showed that a planet of roughly 5 Earth masses on an inclined, eccentric orbit would produce 2 populations over time. One group clusters near the planet's orbital plane. The other gets kicked into perpendicular orientations through a specific set of resonance interactions that unfold over hundreds of millions of years. The perpendicular population is smaller, harder to detect, but it should exist. Ammonite in this reading is evidence for Planet 9. The very object that looks like a counterexample becomes a prediction fulfilled. The trouble is that both interpretations depend on Ammonite's orbit being well measured, and it is not. The object was observed over a short arc, a handful of detections spread across a few years. From that limited data, astronomers extrapolated an orbital period of thousands of years and an inclination that places it squarely in the perpendicular camp. But short arcs produce uncertain orbits. A few more years of observation could shift the calculated path by tens of degrees. The inclination could drop. The semi-major axis could change. The object that currently sits at 90 degrees might, with better data, slide towards 60 or 110. Each possibility tells a different story about whether Planet 9 is real. This is the frustrating core of the entire debate compressed into a single icy body. The most important object in the sample is the least well measured. Every simulation that includes Ammonite treats its orbit as roughly known. Every statistical test that weighs the clustering significance assigns it a position that could be wrong by a wide margin. And because the sample of extreme trans-Neptunian objects is so small, each individual member carries enormous weight. Moving one object reshapes the whole distribution. Tracking programs continue to monitor Ammonite. Each new detection tightens the orbital solution by a fraction. By the late 2020s, the arc should be long enough to pin down the inclination within a few degrees. That measurement alone could flip the entire statistical case in either direction. A confirmed perpendicular orbit strengthens the Planet 9 model because the simulations predict exactly that population. An orbit that drifts back toward the main cluster weakens the perpendicular argument and returns the object to the aligned sample, boosting the clustering signal. An orbit that lands somewhere in between does nothing useful at all. For now, Ammonite sits in a kind of quantum state. It is simultaneously the strongest evidence for Planet 9 and the strongest evidence against it. The resolution depends on data that does not yet exist. Astronomers have spent nearly a decade arguing about an object whose orbit they cannot yet pin down. The stakes are high enough that no one is willing to wait quietly. Papers continue to cite the 90-degree inclination as though it were settled. It is not. The most consequential measurement in outer solar system science is still being refined, one telescope night at a time. Every few years, a new exoplanet survey updates the census of worlds orbiting other stars. The numbers shift slightly with each release, but one finding has held steady for over a decade. The most common type of planet in the galaxy is a super-Earth, a world larger than our own planet and smaller than Neptune. Roughly 30% of stars similar to Sol host at least one. Some estimates run higher. They appear in tight orbits and wide ones, around red dwarfs and around stars nearly identical to the central star in our own system. Super-Earths are everywhere. Our solar system does not have one. Between the rocky inner planets and the ice giants, there is nothing. Earth sits at one end of the mass spectrum for solid worlds. Neptune sits at the other. The gap between them spans a factor of 17 in mass. In most planetary systems observed by the Kepler telescope, that gap is filled, often by multiple planets. The absence in our own neighborhood is, statistically speaking, strange. Planet 9 would fix this. At 4 to 5 times Earth's mass, it falls squarely in the super-Earth category. Its existence would mean that our solar system formed the same type of planet that every other system seems to produce. We just ended up with ours in an unusual location. Flung to the outer reaches by a gravitational interaction with Jupiter or Saturn during the chaotic first 100 million years, the planet exists. It simply migrated to an orbit so distant that it took until the 21st century to notice the evidence. The alternative is that our solar system genuinely lacks this type of world, that whatever process builds super-Earths in other systems did not operate here. or operated differently. This would make our planetary system an outlier among the thousands now catalogued, an oddity requiring its own explanation. Planetary scientists would need to understand why the most common assembly process in the galaxy skipped our star entirely. Both possibilities carry weight. If Planet 9 is confirmed, the solar system joins the majority. It becomes ordinary, a system with rocky planets, gas giants, ice giants, and a super-Earth. The super-Earth just happens to orbit at 500 astronomical units instead of 5. The formation models that explain exoplanet populations would apply here with a minor tweak. One ejection event. One unlucky gravitational kick during the early instability period. Everything else follows the standard template. If Planet 9 does not exist, the question inverts. Why are we different? Why did the disk of gas and dust around the young star produce Jupiter and Saturn and Uranus and Neptune, but skip the most common planetary mass range entirely? The answer might involve the specific timing of giant planet migration, or the total mass of the original disk, or some interaction between Jupiter and the inner solar system that prevented a super-Earth from forming or surviving. Each explanation is plausible. None is confirmed. The exoplanet data creates a strange pressure on the Planet 9 hypothesis. The universe seems to insist that super-Earths should be present. Finding one in our own system, even on a bizarre orbit, would resolve a lingering statistical tension that has bothered planetary scientists since the Kepler mission's first data release. It would mean that the processes shaping our solar system were ordinary, that we are typical, that the only unusual feature is the orbit, which dynamical models can explain. Absence would be harder to explain, and harder to accept for researchers who have spent careers building universal models of planet formation. For the first time in the history of this search, every competing hypothesis makes a distinct and testable prediction. That fact alone separates the current moment from every previous era of Planet 9 speculation. Percival Lowell could not design an observation that would distinguish his Planet X from a statistical fluke. The tools did not exist. The predictions were not sharp enough. Now they are. If a physical planet orbits at the predicted distance, the Vera Rubin Observatory will see it. The telescope's survey covers the relevant strip of sky repeatedly over 10 years. A planet of 4 to 5 Earth masses at 300 to 500 astronomical units would appear as a faint point source, moving slowly against the background stars. The motion would be small, perhaps a few arcseconds per year. But the survey's cadence is designed to catch exactly this kind of slow mover. Detection would require linking observations across multiple nights and filtering out the millions of asteroids and artifacts that populate each image. The software pipelines are built for this. If the planet is there and falls within the survey footprint, Rubin will find it. If the object is a primordial black hole, the prediction changes entirely. A black hole of 5 Earth masses would be roughly the size of a tennis ball. It emits no light, reflects nothing. The only way to detect it is through gravitational lensing or through the rare flares produced when it captures and destroys a small body from the Oort cloud. These flares would appear as brief transient events in the survey data, bright for hours or days, then gone. A pattern unlike any known asteroid or variable star. The Rubin survey's rapid cadence and wide field make it sensitive to exactly these kinds of transients. A primordial black hole would leave a signature in the data that looks nothing like a planet. If modified gravity explains the clustering, there is no object to find at all. The orbital alignment persists in the Rubin data. The clustering signal remains statistically significant even as the sample of extreme trans-Neptunian objects grows from 24 to hundreds. But the survey finds no planet and no flares. The gravitational anomaly exists without a source. This would be the hardest outcome to confirm because it requires proving a negative. Years of survey data showing persistent clustering with no detected object. Skeptics would argue the planet is simply fainter than expected, or outside the survey footprint. But at some point, the non-detection becomes its own evidence. If observational bias created the clustering in the first place, the prediction is simplest of all. The Rubin survey observes the sky uniformly. It does not favor the regions where previous telescopes happened to point. As the sample of distant objects grows under unbiased conditions, the clustering signal dissolves. The orbital alignment that launched 1,000 papers turns out to be an artifact of where astronomers chose to look. The distribution becomes random. The Planet 9 hypothesis joins Planet Vulcan and the canals of Mars in the catalogue of elegant ideas that the data eventually killed. One telescope, 4 hypotheses, 4 distinct outcomes. The observations that will discriminate between them are already being collected. The Rubin Observatory achieved first light and began its survey operations. Within a few years, the dataset will be large enough to test each prediction with statistical confidence that leaves little room for ambiguity. Phan's candidate sits in an infrared catalogue from the early 2000s, a faint source detected by the 2-micron all-sky survey and later cross-matched with the wide-field infrared survey Explorer. Between those two observations, the source moved, roughly 47 arc-minutes over 23 years. That rate of motion is consistent with an object at 200 to 500 astronomical units from the central star. The right distance, the right brightness for something of several Earth masses at the far edge of the solar system. The catch is that infrared catalogues are messy. They contain millions of sources. Galaxies, brown dwarfs, detector artifacts, cosmic ray hits. Cross-matching between surveys taken decades apart introduces alignment errors. A faint galaxy that shifted slightly between catalogue versions could mimic the apparent motion of a nearby slow-moving object. The probability of a false match is low for any individual source. But when you search millions of catalogue entries for objects with the right motion and brightness, even a low false positive rate generates candidates. Phan's analysis accounted for this. The candidates survived multiple filters designed to remove galaxies and artifacts. Its colors were consistent with a cold, distant planetary body rather than an extragalactic source. Its motion fell within the range predicted by the Batygin and Brown orbital models. The probability of a chance alignment producing this combination of properties was calculated at less than 1%. Encouraging, but 1% across a large catalogue still allows for the occasional false alarm. The follow-up is straightforward in principle. The candidate's motion over 23 years allows a prediction of where it should appear in 2025. A modern infrared telescope pointed at that location should detect the object if it is real. If nothing appears, the candidate was likely a catalogue artifact or a background galaxy whose apparent motion was an illusion of measurement error. If something does appear at the predicted position with the predicted brightness, the case becomes difficult to dismiss. Several teams have requested telescope time to perform exactly this observation. The details of the follow-up remain partly unpublished because the competition to be first to confirm or deny the candidate is intense. A positive detection would be the most significant solar system discovery since Neptune. A negative result would be a footnote. The asymmetry of outcomes drives urgency. The deeper lesson is about method. Phan is a graduate student. The data she used has been publicly available for years. Thousands of astronomers had access to the same catalogues. The technique of cross-matching infrared surveys for slow-moving sources is not new. What Phan brought was patience and a specific question. She asked whether existing data already contained the answer that everyone assumed required a new telescope. The approach is almost retro. No machine learning pipeline, no supercomputer simulation, archival data, and careful matching. There is a long history in astronomy of major discoveries hiding in plain sight. Neptune's position was recorded on star charts decades before anyone recognized it as a planet. Pluto appeared on photographic plates taken years before Tomba's official discovery. The pattern repeats because astronomers generate far more data than they can analyze in real time. Archives accumulate, questions change, and sometimes the answer to a new question already sits in an old dataset waiting for someone to ask. If the candidate is real, the discovery belongs to someone who looked at what was already there and noticed what others had overlooked. The cold case solved not by new evidence, but by a fresh pair of eyes on old files. Percival Lowell was brilliant, wealthy, obsessive. He built an observatory in the high desert of Arizona for the express purpose of studying Mars and finding a planet beyond Neptune. His mathematical prediction for Planet X was elegant. Based on observed perturbations in the orbits of Uranus and Neptune, he calculated where a massive unseen world should be. He published coordinates. He directed photographic surveys. He spent the last decade of his life searching. He was wrong. The perturbations he measured were within the noise of the data. The planet he predicted did not exist at the location or with the mass he specified. Clyde Tombaugh found Pluto in 1930, 14 years after Lowell's death, near the predicted region of sky. For decades, this looked like vindication. Lowell's math had worked. But Pluto turned out to be far too small to cause the perturbations Lowell measured. The discovery was a coincidence. Pluto happened to be in roughly the right part of the sky for entirely unrelated reasons. The mathematical framework that predicted it was built on measurements that were simply wrong. The parallel to the current search is uncomfortable. Konstantin Batygin and Mike Brown are brilliant, well-funded, deeply committed. Their mathematical prediction for Planet 9 is elegant. Based on observed clustering in the orbits of extreme trans-Neptunian objects, they calculated where a massive unseen world should be. They published orbital parameters. They directed observational surveys. They have spent nearly a decade searching. The method is the same one Urbain Le Verrier used in 1846. Observe an anomaly in the motion of known bodies. Assume the anomaly is caused by an unseen mass. Calculate where that mass must be. Point a telescope. Le Verrier's prediction led to the discovery of Neptune on the first night of searching. The method produced one of the greatest triumphs in the history of mathematical astronomy. It also produced Lowell's 76 years of failure. The question that hangs over the current search is which precedent applies. Is 2025 more like 1846, when the math was right and the planet was real, or more like 1906, when the math was elegant and the planet was imaginary? The superficial similarities between Batygin and Brown's work and Le Verrier's are obvious and frequently cited. The superficial similarities to Lowell's work are less frequently mentioned. Both used gravitational perturbations to infer an unseen mass. Both produced specific predictions. Both conducted extensive searches that, at the time of their most confident publications, had not yet found the predicted object. The differences matter too. Le Verrier worked with precise measurements of a single planet's position over decades. Lowell worked with noisy measurements that turned out to contain systematic errors. Batygin and Brown work with a statistical pattern in a small sample of distant objects whose orbits are themselves uncertain. The quality of the input data determines whether the mathematical framework produces truth or illusion, and the quality of the input data for the Planet 9 hypothesis remains genuinely disputed. The uncomfortable truth is that methodology cannot tell you in advance whether it will succeed. Le Verrier's approach was identical to Lowell's. The outcomes were opposite. The variable was not the math. It was the data feeding the math. And whether the data supporting Planet 9 is clean enough to produce a Le Verrier outcome or noisy enough to produce a Lowell outcome is the question that no amount of historical comparison can answer. Only a telescope pointed at the right patch of sky will settle it. History does not repeat in astronomy any more than it does elsewhere, but it rhymes often enough to make confident predictions dangerous. On the night of September 23, 1846, Johann Gottfried Galle pointed the 9-inch refractor at the Berlin Observatory toward coordinates provided in a letter from Urbain Le Verrier. Within 1 degree of the predicted position, Gale and his student Heinrich d'Arrest found a faint point of light that did not appear on their star chart. They watched it for several hours. It moved. Neptune. The discovery took a single night. Leverrier had never looked through a telescope to find it. He worked entirely with pen and paper. The planet Uranus was not following the orbit that Newtonian gravity predicted. The deviations were small and precise. Leverrier assumed an unseen planet was pulling Uranus off course. He spent months calculating where that planet must be to produce the observed deviations. He sent his coordinates to Gale. Gale looked. The planet was there. This remains the single most spectacular demonstration of mathematical prediction in the history of planetary science. Nothing before or since has matched it for precision and immediacy. The event created a template, a blueprint that every later planet hunter has tried to follow. Unseen mass causes observable perturbation. Mathematics reveals the location. Telescope confirms. The method worked so perfectly for Neptune that it became the default approach for finding anything hidden in the solar system. Percival Lowell followed the template. He measured apparent perturbations in the orbits of Uranus and Neptune. He calculated, he predicted, he searched, he failed. The perturbations were not real. The predicted planet did not exist with the properties he described. The template that worked so brilliantly in 1846 failed completely in 1906. Batygin and Brown are following the template again. They observe an anomaly. They calculate. They predict. The key difference between their work and Leverrier's lies in the nature of the input signal. Leverrier had decades of precise positional measurements of Uranus. Each data point was a direct measurement of where the planet was in the sky at a known time. The signal was clean. The perturbation was unambiguous. The mathematical inversion from perturbation to planet was well constrained. Batygin and Brown have something different. They have a statistical clustering in the orbital elements of roughly 24 distant objects. Each object's orbit is itself uncertain. The clustering may be real, or it may be an artifact of where telescopes have looked. The signal is not a precise wobble in a single planet's path. It is a pattern in the distribution of a small sample. The mathematical framework that connects this pattern to a planet is sophisticated, but the input is noisier than what Leverrier had. This distinction determines everything. If the clustering is real and unbiased, the mathematical prediction should lead to a planet, just as Leverrier's did. If the clustering is partly or wholly an artifact, the prediction leads nowhere, just as Lowell's did. The method itself is sound. It has been tested. It works when the input data is clean. The open question is whether the input data for Planet 9 meets that standard. The template from 1846 requires one condition that no amount of mathematical elegance can substitute. The anomaly must be real. 84% of the possible parameter space for Planet 9 has been ruled out. Surveys covering different portions of the sky at different depths have systematically eliminated regions where the planet could be hiding. For a casual observer, this sounds like terrible news for the hypothesis. If you have searched 84% of the haystack and found no needle, the needle probably does not exist. But this framing misunderstands how the search works. The 84% that has been eliminated consists of the scenarios where Planet 9 would be closest, brightest, and easiest to detect. A planet at 200 astronomical units with a mass of 6 Earths would have been found years ago. A planet at 300 astronomical units on a low-inclination orbit in the northern sky would have appeared in the Panoramic Survey Telescope and Rapid Response System data. These easy cases are gone. The remaining 16% contains the hardest scenarios. A planet at 400 to 500 astronomical units, a mass closer to 4 Earths rather than 6, an orbit that places it in a region of sky contaminated by the dense star fields of the Milky Way's galactic plane, or a combination of distance, mass, and position that puts it just below the detection threshold of every survey conducted so far. These are the scenarios that survive precisely because they are the most difficult to test. The non-detection has done something that detection would not. It has sharpened the prediction. Each survey that fails to find Planet 9 removes a slice of parameter space. The remaining viable region shrinks. The predicted mass tightens. The distance range narrows. The position on the sky becomes more constrained. A planet that has not been found is, paradoxically, better characterized than it was when the search began. The boundaries drawn by absence are precise. This is the pattern for any search that approaches its target asymptotically. The first surveys eliminate the easy cases quickly. Progress feels rapid. Then the remaining parameter space consists of the hardest possibilities. Each additional survey eliminates less than the one before. Progress slows. The search enters a phase where enormous effort produces incremental gains. This is where the Planet 9 search sits now. The Vera Rubin Observatory changes the calculus because it reaches deeper than any previous survey across a wider field. It accesses portions of the remaining 16% that no prior instrument could touch. Whether it reaches all of it is uncertain. A planet at 500 astronomical units with a mass of 4 Earths at the faintest end of predictions might still escape detection even in a decade of Rubin data. The search would then continue with the next generation of telescopes, and the generation after that. There is a psychological dimension as well. A decade of non-detection wears on the community. Funding agencies ask whether continued searches are justified. Telescope allocation committees weigh Planet 9 proposals against other science. Skeptics point to the empty results and argue the hypothesis has had its chance. Supporters counter that the remaining parameter space is exactly where a real planet would hide. The debate plays out in proposal reviews and conference hallways as much as in journal pages. The 84% figure is not a failure. It is a map of where the planet is not, and that map, through elimination, points increasingly toward where it might be. The most distant, faintest, most difficult corner of the search space, exactly the place where a planet could have hidden for the entire history of telescopic astronomy without anyone noticing. Step back from the individual arguments and look at what has accumulated. Sedna, discovered in 2003, on an orbit so extreme that nothing in the known solar system could explain it. 2012, VP 113, found a decade later on a similarly inexplicable path. The Goblin 2015 TG 387, extending the pattern further. More than 20 extreme trans-Neptunian objects catalogued now, with orbits that reach hundreds of astronomical units from the central star. The clustering of these orbits, announced in 2016, they suggest a common gravitational influence, a mass of 4.4 Earth masses inferred from the orbital dynamics. An IRAS candidate from 1983 that was dismissed as a galaxy and might have been the planet all along. Ammonite, flying at 90 degrees to the main cluster, either destroying the hypothesis or confirming a subtle prediction of it, depending on which simulation you trust. A primordial black hole hypothesis that is physically possible and almost impossible to test. A modified gravity explanation that removes the need for any object at all. A Planet Y hypothesis. If one hidden world exists, others might too. And the Vera Rubin Observatory, now surveying the sky with a sensitivity that none of its predecessors could match. This is not a case with too little evidence. It is a case with too much. Each new discovery over the past 2 decades has made the mystery stranger rather than simpler. Sedna should have pointed directly to Planet 9 if the orbit were well enough understood. Instead, it opened a question. VP 113 should have narrowed the answer. Instead, it doubled the puzzle. The clustering signal should have been confirmed or killed by now. Instead, it sits in a statistical gray zone that allows both believers and skeptics to claim support. The IRAS candidate could have resolved everything 40 years ago if anyone had followed up before the source moved out of the survey frame. Ammonite could resolve everything now if its orbit were measured precisely enough to place it firmly in one population or the other. The Phan candidate could resolve everything within months if the follow-up observations find a moving object at the predicted coordinates. Every piece of evidence points somewhere. The problem is that they do not all point in the same direction. Some favor a planet, some favor bias, some favor something stranger than either. The map of clues looks less like a trail leading to a single conclusion and more like a web of partial connections that resist simplification. The situation resembles a detective case where every new witness adds a contradiction rather than a confirmation. The physical evidence is real, the orbits are measured, the objects exist. What remains uncertain is the story that connects them. A single gravitational source could explain the alignment. So could a combination of observational bias and coincidence. So could physics that no one has yet considered. 20 years of discoveries, dozens of papers, thousands of telescope hours. Multiple competing hypotheses, each internally consistent, each explaining some portion of the evidence while struggling with the rest. And the central question remains exactly as Sedna first posed it. Something is wrong with the outer solar system. We do not know what. The evidence has grown. The mystery has not shrunk. We have visited every known planet in the solar system. Spacecraft have orbited Mercury, Venus, Mars, Jupiter, and Saturn. Probes have flown past Uranus and Neptune and captured detailed images on the way through. We have landed on a comet, touched the surface of an asteroid, and returned samples to Earth. Photographed the nitrogen glaciers on Pluto from a distance of 7,000 miles. The reconnaissance of the known solar system is, by any measure, one of the great achievements of the species. And yet, a planet 4 times the mass of Earth might be orbiting the star right now, completing a single lap every 10 to 20,000 years. Massive enough to tilt the orbital plane of the entire outer solar system by 6 degrees. Massive enough to shepherd 24 smaller objects into aligned orbits. Massive enough to qualify as the 5th largest planet. And we have no idea where it is, or whether it exists at all. The problem is distance. Beyond 100 astronomical units, the solar system is unexplored territory. Voyager 1, the most distant human-made object, is about 163 astronomical units from the host star after nearly 5 decades of travel. It has passed through that space without encountering anything, but Voyager's path is a single thread through an enormous volume. The space between 100 and 1,000 astronomical units from the star is vast. Millions of times the volume of the inner solar system. A planet at 400 astronomical units could sit for billions of years without any spacecraft, passing within 1 billion miles of it. We have better maps of galaxies millions of light years away than we have of our own backyard at these distances. The Hubble Space Telescope has imaged galaxies at the edge of the observable universe in extraordinary detail. The James Webb Space Telescope peers into stellar nurseries thousands of light years distant. We know the chemical composition of atmospheres on planets orbiting other stars. We can count craters on moons of Jupiter from Earth orbit. The technology for seeing far away is extraordinary. The technology for seeing faintly nearby is different, and it has lagged. A planet at 400 astronomical units is faint because it is cold, and because the light it reflects from the star falls off with distance to the 4th power. Double the distance, and the reflected light drops by a factor of 16. At 500 astronomical units, a super-Earth-sized planet would be dimmer than magnitude 26. Visible to the largest telescopes on Earth, only with long exposures and careful image processing. Lost in the noise of distant galaxies and detector artifacts that populate every deep image. The outer solar system is not hiding this planet through any exotic mechanism. There is no cloaking device, no unusual physics. The planet, if it exists, is simply too far away and too faint for the surveys conducted so far. The same laws of physics that allowed us to photograph Pluto in exquisite detail with New Horizons, guarantee that an object 20 times farther away will be millions of times harder to detect from Earth. The darkness of our ignorance is proportional to the fourth power of the distance, and the distance is very large. If Planet 9 is real, then every textbook diagram of the solar system published in the last 400 years is wrong. Every model that treated 8 planets as the complete inventory missed one. Every simulation of solar system dynamics that did not include a 5 Earth mass body on a distant eccentric orbit was incomplete. The 6-degree tilt of the solar plane that astronomers noted and never explained was a signpost that everyone walked past. For the entire history of telescopic astronomy, from Galileo forward, a world larger than Earth has been orbiting the star and no one knew. If Planet 9 is not real, then 2 centuries of mathematical planet hunting have produced a pattern of failure interrupted by a single success. Leverrier found Neptune. Everyone since has found nothing. Lowell's Planet X, the trans-Plutonian planets of the mid-20th century, the various Planet 10 hypotheses of the 1980s, and now Batygin and Brown's Planet 9. Each generation brought better math and better telescopes. Each generation was certain the clustering in the extreme trans-Neptunian orbits would join the canals of Mars and the luminiferous ether as patterns that intelligent people were sure they saw, and that turned out to be artifacts of imperfect observation and eager interpretation. Either outcome unsettles the foundations. A discovered planet rewrites the architecture of the solar system and raises immediate questions about what else might be hiding in the dark beyond Neptune. A confirmed absence forces a reckoning with how easily statistical patterns in small datasets can mislead even the most careful researchers. The Vera Rubin Observatory is surveying. Its data accumulates nightly. Somewhere in the growing archive, the answer either exists as a faint moving point of light or does not exist as a conspicuous absence. The Phan candidate will be followed up with modern infrared telescopes pointed at its predicted 2025 position. Within months, it will be confirmed as a moving object or dismissed as a catalogue ghost. Ammonite's orbit will be refined with each new observation, and within a few years, its inclination will be pinned down tightly enough to test the perpendicular population prediction. The tools exist. The observations are underway. The timeline is short by astronomical standards. 5 years, perhaps 10. Enough for Rubin to complete its first full survey pass, and for the extreme trans-Neptunian object sample to grow from 24 to hundreds. But every generation of planet hunters has believed it was the one that would finally settle the question. Lowell believed it. Tombaugh believed it. The astronomers who searched for Planet X through the 1970s and 80s believed it. Certainty about an imminent answer has been the one constant in a search defined by its failure to deliver one. The 9th planet is the oldest open case in planetary science. The file has been active since 1846. It has survived the discovery of Neptune, the discovery and demotion of Pluto, the invention of digital surveys, and the cataloguing of thousands of worlds around other stars. It may survive the Vera Rubin Observatory too. The next telescope will be more sensitive. The sample will be larger. The statistical tests will be sharper. And the question will still be there, waiting at the edge of what we can see, just beyond the reach of the current generation's best instruments.